Seated binomial expansion explanation part 1. So in this topic we're going to learn how to use Pascal's triangle to expand the expression of the form a plus b to the power of n. We're also going to learn how to use a combination of and factorial notation to expand the expression a plus b to the power of n. And we're going to use the expansion of 1 plus x to the power of n to expand a plus b to the power of n. So as you can see, this a plus b to the power of n is going to be a very important part of this topic. So this is actually a binomial product, which is the expansion of the form a plus b to the power of n. So such expansions crop up everywhere in mathematics as we often need to expand them. So suppose that we wish to expand a plus b to the power of 3. So this is a plus b to the power of n, where n is equal to 3. So this can get rather long and tedious when we have to expand each bracket in turn. So let's do it for an example of how long it takes. So we have a plus b to the power of 3. Well, that's the same as a plus b times a plus b times a plus b. So if I expand out one set of this brackets, I'll have a plus b still for the first one, and for the other two, when I expand them out, I'll get a squared plus 2ab plus b squared. Now I need to expand it out with this bracket as well, so I'll get a cubed plus 3a squared b plus 3ab squared plus b cubed. Now I've got this from expanding out these two brackets and collecting the like terms, so it does take even longer than what it just has. But imagine if we were using up to the powers of a plus 4 to the power of 4 or a plus 4 to the power of 10. There must be a shorter way of finding out what it is when it's expanded than to multiply out the brackets individually. So, in such expansions, like the one we've got here, we can see that the powers of a decrease. Here we've got a to the power of 3, then in the next term we've got a squared, then a, and then we have no a value at all, but that is equal to a to the power of 0 because that just gives us 1. And we can see that the powers of the b terms increase. Here we've got no b, but that means we've got b to the power of 0, and then we've got b squared, b cubed. So therefore, we can create a shortcut for the expansion of such expressions. All we need to do is find a quick method of finding the coefficients. The coefficients are the terms before. So here it'd be 1a cubed, 3a squared b, 3ab squared, and 1. So it's 1, 3, 3, 1 for this example. So we need to find a way of finding the coefficients for a regular sequence of expressions. So this is called Pascal's triangle. So in Pascal's triangle, it is laid out in the form set out in the form 1, and then below it I'm going to have a 1 again, and then another 1, and then below that I'm going to have 1, and then I'll do 1 plus 1, which will give me 2, and then I'll have another 1 at this end. I'm going to carry on doing that, so that here I'll be doing 1 plus 2 gives me 3, 2 plus 1 gives me 3, and then I'll have a 1. So next row will be 1, 4, 6, 4, 1. And it becomes easy to see where this triangle comes from, just adding up the two values directly diagonally above. So here We are told Pascal's triangle is used to find the coefficients for a plus b to the power of n. And it is a triangular array, as we can see here. So the first and last terms in each row are ones. So that's the first and the last term in each row. And the other numbers are found by adding together the two terms diagonally above them. So to illustrate Pascal's triangle, we're going to first of all suppose that we are trying to expand a plus b to the power of 4. So we know from the previous page that this means that we are going to have some coefficient, and then we'll have a to the power of 4 plus some coefficient a to the power of 3, b, plus, and carrying on doing this, making sure that we decrease the power of a by 1 each time and increase the power of b by 1 each time. So here we'll have a, b cubed, plus some coefficient b to the power of 4. So how are we going to find these coefficients? Well, we're going to have a look at the fourth row in Pascal's triangle. And as you can see here, these are the coefficients that you get. So the expansion that we'll end up with is 1, a to the power of 4 from this part, plus, next one we've got is 4, so 4 will go in here. So we have 4, a cubed b, plus, next one we've got is 6, that'll be 6, a squared b squared, plus, got another 4, so that'll be 4, a b cubed, and then we'll have plus 1 b to the power of 4. And of course, the 1 a to the power of 4 and the 1 b to the power of 4 can just be written as a to the power of 4 and b to the power of 4 respectively. So, Pascal's triangle provides a shortcut for finding the coefficients in a binomial product. But even Pascal's triangle can get tedious as the number of rows is very large. So if we had to find a plus b to the power of n, and n was 30, we'd have to keep doing this all the way down to the 30th row, making large numbers and a lot of work for ourselves. So we're going to try some examples using Pascal's triangle, and then try and see if we can find a better way of finding the coefficients in a binomial product.